Hi, so I'm going to take you through the proof of the range equation. This equation comes in handy when we're trying to especially figure out a launch angle, but it comes at a price, and we'll see this in the derivation, but I want to point this out right off the bat, that this equation relates launch velocity, launch angle, and horizontal range if and only if the launch height is equal to the landing height. And so that's a big if, and we'll see that come up in the derivation. Another way of saying that is that delta y over the whole trip equals 0. All right, so let's just sketch out what's happening in the situation that this equation describes. So we have that's not horizontal. We have a horizontal plane, and an object is launched at a launch angle vi, no, launch velocity vi, at an angle theta from the horizontal. And the question that we're trying to answer is how far does it travel horizontally before it strikes the ground? So it's going to travel along that parabolic path, like so. Okay, now we know we really only have one equation for horizontal range. And that is kind of strange, first of all, that we even call it range, because I know in math class range is a y piece of information. In physics, its range is horizontal. So the range equation in general is delta x equals vx times t. And the problem right now is this t element, because if we look at what we're trying to only have in our equation, we only want the launch velocity and angle. And so we're going to have to find a way to replace t with some other stuff. Vx, of course, we know is vi cos theta. That's no problem, because theta is measured from the horizontal. But let's set aside some time to find t. So we're going to start with the final velocity equation. And with this equation, here's where that condition comes in. So if delta y equals 0, that's a big if, then we can say that the final y velocity is equal to the opposite of the initial y velocity, because whatever speed it loses on the way up, it gains on the way back down. And we also know that viy equals vi sine theta. That's that vertical component of the right triangle. Maybe I'll take just a moment to draw that out. So here's vi, here's vx, and here's viy, and here's that angle theta. So we see that viy is opposite, and so it's vi sine. And so if this is true, if delta y is 0, then the final y velocity and the initial y velocity are opposites, and we can rewrite that pink equation replacing vfy with negative viy. All right, so now our goal is to isolate t. Again, we know that viy is vi sine theta, so this becomes negative 2 vi sine theta equals ay times t. We do know that ay is negative g. This is free fall. We're going down the negative direction. And so we can then isolate t, plug in negative g for a. So this becomes negative 2 vi sine theta all over negative g. So those negatives go away, right? All right, so this is a handy little tool. I don't suggest that you memorize it, but it definitely can come in handy. Again, though, remember that this has that big if. So now that I have an expression for the time, I can revisit my initial blue equation and replace t with this new expression. So just to rewrite, delta x equals vx times t. So that means that delta x equals vi cos theta times this equation 2 vi sine theta all over g. So really we're done, but it's kind of yucky. So let's clean this up. So first of all, I'm going to combine all that stuff in the numerator. So this becomes delta x equals 2vi squared sine theta cos theta all over g. And now we're going to take advantage of a trig identity that some of you may have met already. So we see 2 sine theta cos theta in that numerator. Well, that's the same as sine of 2 theta. Let me write it the same way. And so I'm going to rewrite this equation one last time, replacing 2 sine theta cos theta. Delta x equals vi squared sine 2 theta all over g. So this is a great equation. It's especially handy if we're looking for theta, actually, because it's almost impossible to, well, it's not almost impossible, but it's a big, humongous pain in the butt to find theta. Boy, I do not love that rectangle, but here we are. You can use it to find theta, you can use it to find vi, you can use it to find delta x if delta y equals 0. Because, as you might have picked up, this students sometimes start using this in situations where it's not applicable. So if you have a situation with a cliff or a situation where a projectile is launched onto a building from the ground, this equation will not work because baked into it is this assumption that delta y equals 0. All right, that's all I got.